Alrighty. We're going to look at things of the following form today. Better pen than this. So, okay, the A's are constants. These are not functions, and that is very important. If they're functions, it's a completely different process. So we're looking at nth order linear homogeneous constant coefficients. We are particularly going to focus on second order, but I'm going to show you how to do all orders with our main focus is second order. Okay, everybody with me on that? Now, here's what we do know. Because of the coefficients are constants, that means when I'm taking all my derivatives of things and I have only constant coefficients, things have to add up in such a way that everything cancels. You know, if my functions are just trig functions in general, or square roots in general, remember these are constant coefficients, or just think of functions in general, things are not going to cancel out. What type of function ends up looking like its own derivative over and over and over and over again?
E to the x exponential.
Only e, yeah. So what we're going to do is we're going to say, let's assume that e to the mx, where m can be any real number, we're going to start with reals, and then we're going to look at all the cases. Let's assume that our answer has this form, and it's actually not a stretch, because all the derivatives of this look like this. So if I put all the derivatives of this in there, what I'd get is a whole bunch of multiples of e to the x, or in this case, e to the mx. So does that make sense? This is the general rule for this. So now let's look at the particular. Very specifically, we're going to look at this problem. And I will do extensions. I will do higher levels, but not yet. A0, oops. Oh, did I write the, sorry. I'm off by one, my bad. This should be dy dx, and this should be y. Sorry. 0th derivative, 0. Okay. That didn't look quite right. So if we say, let's start by letting y be this, then what's the second derivative? Wouldn't that be m squared? Huh. E to the mx. And then what would the first derivative be? Just m e to the mx, and then the function itself, a0 e to the mx. Now if I factor out the e to the mx, then I get a2m squared plus a1m plus a0 all times e to the mx equals 0. So far so good?
Yeah.
Well, that can't be 0.
Right.
So that means that only a2m squared plus a1m plus a0 equals 0. But that's simply a quadratic equation in M. That absolutely is guaranteed to have solutions. Ooh. Everybody cool with that? I'm guaranteed to have solutions. Now, there's 3 possibilities. What are they? Remember? 2 real.
2 real or 2 complex?
2 complex, or 1 repeated real solution. And that all depends on the, what's the D word?
Discriminant.
Discriminant, good. I was glad you didn't say determinant, because I get a lot of people get those backwards. So we're going to look at problems of this nature, and it turns out these are just generally not that bad. The very worst you're going to have to do is solve a quadratic equation using your quadratic formula. Now, what you're going to find, it is often the case. It is often the case that you're going to be given a lead coefficient of 1. It doesn't have to be, but that's probably the most common problem. So let's start with one that looks like that. So I've got d squared y dx squared minus 3 dy dx, oops. Let's say minus 28y equals 0. So I start by saying, let's let y equal y equals e to the mx. Okay, then what is this going to be? Now, this equation right here, we give it a name. It's called the auxiliary equation. And you're often asked for that particular equation. It's the equation that you're going to determine your exponents with. Now here's the beautiful thing. Do I need to physically take two derivatives of this, take one derivative of this put this back in, factor out the e to the mx, and then get my auxiliary equation?
No.
Or can I write it as the next thing?
Next thing.
Yeah, always just write it as the next thing, sitting right in front of you. Because I just gave you the, it's right here. It's always gonna look like this. Well, in this problem, what was my A2 in this problem?
1,
And what was my A1?
negative 3,
-3,
And my A0?
negative 28.
-28.
So let's do that. So what is this gonna be? M squared?
Minus 3m minus 28 equals 0.
Okay, question. Did I already answer it? Okay. I like those kind of questions. Does this factor nicely?
Mm-hmm.
Or I'll do
Yes.
my part. I'll do my part.
Yes.
Okay.
It's a 7 and a 4, so it's a -7 and a +4.
So what does that mean? That means I have two solutions. One of them we'll call it y1 is e to the 7x. The other one we'll call it y2 is e to the -4x. Does it matter what order I put them in? No, just the order you factored. These, because there's only two, are these linearly independent?
Yes.
Because they're not, what? Do you remember? With two, it's easy. They're independent or they're multiples.
Okay.
And they're clearly not multiples, so they must be. It's when you have three or more that it's not as obvious, but there's only two. So we've done everything correct. What would the final answer to this be? Would this be the final answer? I'm saying solve the differential equation. So what do you think?
Add
The
them
sum
together.
of the solution.
So would it be, would this be the answer?
plus some coefficients, right?
Oh, probably yeah, probably that. Could either of the coefficients turn out to be 0?
Yes.
Do we start by assuming they're 0? No, that'd be a bad idea. How would I ever determine them?
Initial
Initial.
conditions.
Yeah, if I don't have initial conditions, I walk away. If I have initial conditions, I calculate both of them. It's that simple. Is there a way to check this? Yeah. Just do this. Take two derivatives of this. By the way, do I have to do it as a whole, or could I check them one at a time?
One at a time.
You can, because if I do two derivatives of this, it'd be like breaking up your derivatives anyway. So you can certainly check them one at a time. There's only one error in this problem. There's only one error. What do you think it is? Right there. Pluses and minuses. That's why it's not a bad idea to check. But in actuality, I don't really need to check it here. I could really just check it here, couldn't I? Isn't that nice? So, as a general rule, this problem becomes absolutely a piece of cake.
So this only works when we have second order differential equations.
This only works.
Oh, sorry.
It's kind of vague.
To plug these
No,
coefficients
this
into
is
the
for
auxiliary equation.
No, this is for
Any type.
every possible thing if I have constant coefficients. We concentrate on second order, not only because it's ridiculously common to do second order, but think of the algebra. I'm getting quadratics. If it's a higher order, I'm getting higher degree. And that might be more difficult. Now, are there third degree or fourth degrees that you can solve? Yeah, sometimes I can. Sometimes I have easy ones. Let me do an example of one. Let's do, how about, hold on a second. No, I can't. Sorry, that should be an 8. I can't do math in my head anymore. Oh, this one looks beyond difficulty. Maybe. So if I start with this, then what will my auxiliary equation be?
M to the third plus 6m squared
6 m squared, everybody okay with that? Plus,
plus 8m
Equals
0.
oh, I can't, or wait a minute.
M equals 0.
Oh, maybe I can do this one. I said sometimes you can do a higher level one, this would be a perfect example of when you can do a higher level one. There was no y term, which meant there was no constant term, which meant that it was not that bad of a factor.
Before you go on, you were saying earlier about how that problem, the signs were wrong. Can you explain that?
No, I said the only error anybody ever makes is getting the signs wrong because they
okay.
factor badly.
Oh,
No, that's what I'm saying.
Oh,
We get going really, really fast, and do we ever make that mistake?
Yeah.
If everybody in the class did that independently, you think we're gonna be 100%? I'd be surprised if we were more than 80% because we're doing this really fast in our head, and getting the plus or minuses backwards is so easy to do. I don't want you to do that. That's just the single most common error. Nothing to do with your ability to do the problem. It's just an arithmetic error. So there is a check, but you really only have to check it here. But by the way, please, I just gave a Calc 2 exam today, and I have people that were just off the charts, great. But they were sometimes from one step to the next, their signs were changing. They didn't mean them to, but they changed, which completely changed everything. Can you imagine doing things like a partial fractions decomposition and having the sign change? You know, changed all your coefficients then. So what are my roots of this?
2 and 4.
-2, -4, and 0.
So how about 0, -2, -4? That's why I got it. I said the plus or minuses are where we might make a mistake. So I'm going to have 3 linearly independent solutions. Bless you.
Thank you.
It's going to trouble you at first. So the first one will be e to the
0.
0. The next one?
E to the -2.
And the next one? E to the 0. What's that?
1.
Okay.
Oh,
Does that seem weird?
no.
So therefore, what is my final answer?
C1 plus C2 e to the negative.
Yes, I have to have that term in there.
Mm.
Cool. Now, that one's the easiest one to check. Pick any real number. Now take 3 derivatives, 2 derivatives, and 1 derivative, and it's going to be 0. So you know it's going to work. Now, I would need initial conditions, of course, to find the coefficients. I'd actually need 3. But that's how it, okay, so that's not a problem. This is going to show up occasionally, things of this nature. Okay, you're solving a quadratic. Primarily, that's what our main thing is. We're not trying to do cubics in general. This was exceptional. So I need to show you something. I don't ever need you to do the next thing I'm going to do because it's really horrible and ugly. It comes from the reduction of order section. But there's a situation that can come up where we don't know exactly what to do. So let me give you the situation, okay? So keep it really simple. You have d squared y dx squared. How about minus, I don't know, 10 dy dx plus 25y equals 0. Now, I am really lazy, and when it's understood in every problem we're saying the solutions of the form y equal e to the mx, that is true. I'm doing that all the way through. Can I literally write the auxiliary equation right now?
Yeah.
What would it be?
M squared minus 10m plus 25.
Plus 25, piece of cake. And that's, ooh, I like that one. So that gives me m equals 5, and then in the higher levels we like doing that. There's a word. Do you ever know what the word is? When you have a repeated factor, we say it has multiplicity. For those of you who've done eigenvalue, eigenvector problems, when you had a repeated eigenvalue, you say it had multiplicity too. Because why? An nth degree polynomial equation actually has to have n solutions, but some can be repeated, and that's how. Okay, so y1 is e to the 5x, and then y2 is obviously e to the 5x, right?
Wait, you're,
I think those might be linearly dependent.
Mm-hmm.
You guys see a problem with this?
Yes.
It appears that we only have
One.
one. You have to have 2. It's the how to find the second one that I'm going to show you. And the way to find it's horrific. The result is easy. I don't need you to do the derivation. I need to show you the derivation so that once and for all. Now, in the reduction of order section, the author showed you there is an alternate way of finding the second answer. You don't ever actually want to do this, by the way. There's an alternate way. And I'm just going to really quickly do the Reader's Digest version because it's not a technique that you actually want to use in general. It's too long, it's too messy, okay? So, I'm gonna write it down because I wrote down, even when I looked in the book, I go, God, that's awful. So I have the problem, the original problem was of this form. This is going back a bit. And we said we know y1, and then y2 is going to equal u times y1. You guys remember doing that? That was last day. So when I do that, I'm going to go, and eventually I'm going to get something of this form. I'm going to put dot, dot, dot. After I make that substitution, I'm going to get y1, second derivative, plus 2 dy1 dx plus p of x y1 du dx, and that's all going to be 0, and then I'm going to do my substitution. That's going to become dw dx. That one's going to become w. And somebody asked this question last day, and it is a correct question. The way we were doing the problem primarily was I was treating them all as first order linear, which they are. But every time you have a first order linear, off to the side, first order linear, that's first order linear. What if that's 0? It's still first order linear, but if I throw them on the other side, isn't that like the easiest separable? First order linear isn't always separable. First order linear homogeneous is always separable. And when we're doing this problem, you're always making it into a first order linear. You're always making it. So could I do this as a separable instead? So, by the way, did anybody on the quiz do this as a separable? You could. You could. First order linear in general, no. But if that's a 0, then this is a really easy separable. That's all I'm saying. And somebody asked that question, I believe, in class last day. Might have been you, I don't know. That hey, isn't that also separable? Yes. Yes, it is. And you're not going to get a different answer. And I don't even think it takes a different amount of time. So if I think of this as a separable now, it ends up being really, really icky. Okay, so the form that I'm going to get when I do this, I'm going to end up getting something that looks like this. 1 over w, I'm assuming I've made this substitution. So you're going to divide everything through by y1. So let me do that first. That one's just gone, okay? So I'm going to have this plus and I'm going to break these into 2 different terms. Throw that on the other side. Make sure I got this. Okay. It's this guy here that gets kind of goofy. Isn't that then just 2 over y1 dy1, dy dx dx? So now what I've got here is log w plus log 2y1 equals this integral. But if I put those together, it's now log of 2wy1 equals this. And here's where it really gets horrible. So therefore, 2wy1 equals e to the negative p of x dx. Because I don't have p of x yet. I don't know what that's going to be. This kind of looks integrating factor-ish. So now, what does w equal? Oh, sorry.
Isn't that 2
I'm sorry. I want to.
Yeah, that one.
Sorry.
Squared.
My bad. Sorry. 2 there. Sorry.
Yeah.
So that
Okay.
I can't read my own writing. Yeah, the 2's on the outside, not on the inside. So let me fix that. So now I've got this equals 1 over this times e to the this. Okay, that's not the worst thing in the world. It's about to be, because isn't this du dx? So now what does that mean u equals?
The integral.
The integral of e to the integral. Okay, I'm saying, this is what I was saying before. Nobody in their right mind would try to do this as a way of finding the second thing. I'm just saying it is. So now, let's go back to the problem and say, what if I have a repeated root? What if I get the same value twice? I solved my quadratic and I got, let's just call it M1. but I got it twice. Then it turns out this is where I didn't shorten it. This is actually everything. From here to here, you have the notes. We did this in class. Remember, all this stuff in the middle canceled, and then we got something that looked this awful. Nobody in their right mind would do this as a way of solving it. But I need this result to figure out what the second solution is, because what's the first solution? The first solution is my e to the mx, or call it m1, m1 and m2. Okay? So what I've got then, if I let's see, I lost the term, hold on a second. Oh, this is the u. Okay, so then the y2 was y1 times u. So I now have to put an e in front of this. So my second solution is going to be, let's call it m1x. That's the one I just found. In that problem, that's the 5, e to the 5x. All right? But then when I put those things in here, this is going to be e to the m1x squared. When I'm squaring the whole quantity, don't I just multiply this by 2? And then on top, when I perform that integration, I actually get the exact same thing. This is going to give me exactly that. Huh. Sorry, that's m1. Isn't that just 1? So what's the antiderivative here?
X.
That's the second solution. It's actually that easy. Oh, you're kidding me. Yeah. So when you have a repeated solution, let me go back to the problem we just did. We found y1 was e to the 5x. So what's y2 going to be?
X e to the first.
And if we check it, let's actually physically check it, because this is very wise. There's going to be many times in this class where you thought you did everything right, and maybe there was a repeated solution and you just didn't see it. You didn't realize it was repeated. Or you got something and you're saying, well, how do I know that this is the right thing? Well, it has to work. Let's take two derivatives of this. So dy2 dx is first times derivative of second plus second times derivative of first. Then the second derivative of this, first times derivative of second, second times derivative of first, and then the derivative of this guy. So that's 10 of these then. Now let's put all of this back into the original question, which, sorry, I erased everything. My original problem, I believe, was this. Is this correct? I think that was the original, because we got 5. That's how I remember. I'm not that clever. Believe it or not, when I'm designing the questions, it's actually really easy. I'm just looking at the coefficients and thinking quadratics. So I would have 25x e to the 5x plus 10 e to the 5x, that's my second derivative, minus 10 of these, so minus 50x e to the 5x minus 10 e to the 5x plus 25 of these. So if I didn't totally mess that up, does that work?
Mm-hmm.
Now, when you add these up, let's see, these guys cancel. Okay, and then I have 25 of them minus 50 of them plus 20, and that all cancels, and I get 0. Is that a good thing? That's a great thing. It was supposed to be 0. That's how I know I did it right. So, when you have a repeated solution, this is what you get. What if? What if I have a second repeated solution?
X squared e to the 5x.
You just keep going. That's exactly correct. There's a different formal proof that I'm going to do next day that shows that it's a completely different way of looking at it. It doesn't help to have the formula we just did, but when you have multiples, it's okay. So what if my auxiliary equation ends up being, x minus 5 quantity, to the 4th power? Well, then I'm going to have e to the 5x, I'm going to have x e to the 5x, I'm going to have x squared e to the 5x, I'm going to have x cubed equal to 5x, because those are all linearly independent solutions. Because of that, each of those have a power of x. So the repeated one is the hardest one to derive, but it's actually incredibly easy now to perform because you don't need to ever derive it again.
So you're saying if we have a repeated solution, just slap an x on one of them and then just increase the power by 1 if you have
Every
multiple.
time it keeps showing up.
Thank you.
How do you
This-
know when to stop?
I don't know, it's fun, so you know. But you have to have exactly the same number of solutions as the degree of the problem. So
Okay,
hold that
so
thought. Let me go back to a problem similar to one we just did a moment ago. Okay, so how about I have something like this? Let me take that one, but let me now make it fifth. Oh my gosh, this is just completely out of control at this point. Minus 10 times the fourth derivative plus 25 times the third derivative, and then I'm going to stop. You don't mind this one because in the end it's still only going to be a trinomial, isn't it? Yes. If the solutions in general are of the form y will e to the mx, I do that to find the m's. Then what is my auxiliary equation here?
M to the
M to the fifth
Minus 10m to the
fourth plus 5m.
If I factor out the m cubed, would it be legal to write this way? Stare at that for a moment.
Yes.
Is that correct? Listen. Is that correct?
Mhm.
Yes. So I can say then that we'll call M1 equal to 0 with multiplicity 3, M2 equals 5 with multiplicity 2. So what are my linearly independent? Here's when you said, how do I know when to stop? This is how I know. I have to have 5 solutions. That's the most important part. The degree of the differential equation is exactly the same as the number of linearly independent solutions. That's why in the previous example, I couldn't say e to the 5x twice. Because they're not linearly independent. And then it gives the illusion I only have one answer. So won't this one be e to the 0x? But then what's the next one?
X equals.
X e to the 0x, x squared e to the 0. Oh, and then the next one, e to the 5x, and then x e to the 5x. So obviously replace e to the 0x with 1. So do I have 5 linearly independent solutions?
Yes.
Yes, I do. Those who've had linear algebra, the polynomial space. Let's just say P3, that's polynomials of degree 3 or less. It's a 4, right? It's fourth degree. Why? Because I have constant linear squared cube. And so if you were finding the standard basis, well, x cubed for the cube, x squared for the squared, x for the x, but what do I do for the constant?
X is 1.
You used a 1. Oh, then every single polynomial would be a linear combination of the, okay, that's why. Well, this is really, really similar in that regard.
I was just wondering what your thinking was when you said x squared e to the 0x instead of just saying, okay, we have e to the 5x, then x e to the 5x, and then
Well,
x squared.
okay, because I've got 3 different e's with this exponent, and I have 2 different e's with this exponent.
Right.
So that's why I wrote 3, but the first repeat got an x, the second repeat got an x squared. Now, obviously, you're going to write just equals x squared. But I'm showing you how
sorry,
to
that-
justifying those answers.
It's a multiplicity of 3. I
Yes.
was, okay.
And each of, when we write it all together, each of those 5 terms will have their own constant.
Yes,
So,
yeah,
if
that
it-
definitely make sure you have 5. So what would it be? It'd be C1 plus C2x plus C3x squared, and so on. That's called give me the general solution. A lot of times you're just asked, give me all the linearly independent solutions. Boom. Give me the actual general solution. Now you're just writing it as a linear combination. There's not more work involved. But the difference is, I can't give you the final answer with initial conditions unless I give you the general solution. Because if I leave them like this and there's initial conditions, then I won't be able to find the constants. So depending how the question is asked. You know, if I just say, give me all the linearly independent solutions in something that looks like this, the final answer, give me the linear combination of this. That's not more work, as you know. But always do those first to make sure that you didn't accidentally repeat something. Now, there's one more case. What's the one more case?
You said this
We just did 2 reals. We just did 1 reel repeated.
Oh, it's imaginary. Oh no.
Yeah, or complex in general. Ooh.
Oh.
That's the gnarliest one. That's the one that's going to require a little bit more algebra.
You said this was a linear combination of solutions, or no? You called this a
those are my linearly independent solutions. Your final answer would be a linear combination of those. That's what you're bringing in the arbitrary constants. Okay. Oh boy. So this is where it gets a little bit dicey. So I'll give you a little bit of background just to remind you. Okay. When I go through this in my other classes, we did Euler's method the other day. That's very specific, and that's very, very specific just to what we're doing, but that's not used on the broad scale. This one really is. I always remind people how important this one is. I'm a huge sports fan, as many of you know. I mean, my two favorite sports are football and hockey. In fact, oh gosh, great game last night for the Kings. Talbot gives up a goal on the first shot of the game 15 seconds in, then stops 30 straight, and they blew him out 5-1. It was awesome. There are 2 professional sports franchises in North America where the owners were huge math guys. Everybody knows that. Okay. One of them used to be the football team in Houston that moved to Tennessee, and the other one's the hockey team in Edmonton that Wayne Gretzky played his best days in. Both of them were named after. What is the Edmonton hockey team? The Edmonton Oilers. And what was Houston's name? The Houston Oilers. Yeah, that's how important this formula is, that 2 of the biggest sports franchises on planet Earth were named after this guy. I'm serious. They're called the Oilers. So I think their logo should have been like an imaginary number or something. It would have been way cooler. But what is Euler's formula?
E to the I theta equals cosine theta plus I sin theta.
Now, the irony is, when we write a complex number, don't we usually write it in the form a plus bi?
Mm-hmm.
So why do people put the I there? There's actually, it's a practical thing. It really doesn't belong there, but here's the reason. Okay, think in Calc 1. Is my argument x or is my argument xy, or is the correct answer? I can't tell.
Can't tell.
Yeah, what if my argument is xy, what should I put there? Parentheses. But if my argument's only x, then where should the y be?
in the front.
In front. That's why this is really bad notation. So, that's correct. But is my argument theta, or is it theta I, or is the correct answer can't tell? Well, the first thing people say is, well, you're not going to, like you're going to have an imaginary angle. You have an imaginary angle exactly 50% of the time. In everything that exists in the real number world, you have an imaginary angle 50% of the time. So no, theta I is actually very common. Oh, so if I meant cos theta times y, I actually will write it this for readability. We put the I in front just so there's no possibility of confusion, right? Everybody's okay with that. Also, the fact is that nobody writes this, but that would be a good way of doing it. So that's Euler's formula. Where does that apply? That applies on the unit complex circle. That's the circle of radius 1. Okay, well, I know that ordered pair is cos theta comma sine theta, correct? Oops. Why? Because it's a unit circle. That's the ordered pair. But you guys know this, well, okay, maybe you don't know this, but maybe you've been exposed to this. This is the imaginary axis. This is the real axis. Every point out here represents a unique complex number. What complex number is represented by the point A, B? That's the complex number that's represented on the complex plane. Okay, this is actually the way the world works. You may not have been exposed to this tremendously, but from now on you kind of need to be, because it's always been, we've been mostly working with purely real numbers though. So if that's the case, then, oh, okay, this is the same thing. Then what value does this represent on the complex plane? Clearly, cos theta plus sine theta times I. Oh, okay, same thing. But because it's of length 1, it makes it a little bit easier. And we call this is e to the I theta. Now, the reason this is so huge is I can solve so many problems this way. I just want to remind you, This is something you hopefully did, let's say, in a pre-calculus class. Start with something simple. I have 1 plus 1 times I. And I want to raise that, I don't know, let's say to the, just for fun, the 16th power. Just because we're out of control. That's what we do. That's a binomial. I could do that. It'd be really nasty. Well, let's see. 1 plus 1i. Isn't that 1 comma 1?
Yeah.
So isn't that 45 degrees or pi over 4? And wouldn't that be root 2? So couldn't I rewrite this as root 2 times the cosine of pi over 4 times I sine of pi over 4? And now raise that whole thing to the 16th power. Okay, well, that didn't make it any easier. Yeah, it did. Because this is e to the I pi over 4. So this is now root 2 to the 16th, which is 256. And this is e to the 4 pi I, which is 1. So the answer is 256. It's actually that easy if I have a nice common angle. This is something hopefully you saw in a pre-calc class. It comes from de Mott's theorem and a lot of other things. Is this life and death? No, but this is most people's first exposure to this. You're going, man, that is so cool. Well, it was only cool because I had a nice angle. If the angle wasn't nice, not as cool. Okay. But it's using this. This formula relates real to complex, circles to triangles to hyperbolics to exponentials to logs. They're all related by one formula. So how does this help me? We're trying to do e to the mx. What if my m's are complex? That's the point. So what if I'm doing a problem, and we'll do some specifics, but I solved it and my m, let's say, was alpha plus or minus beta I, where alpha and beta are real. 2 plus 3i. Because right now we're only doing real coefficients, and that is actually important. If we were allowed for complex coefficients, this gets much harder. Could you imagine doing an eigenvalue, eigenvector problem where all the numbers in your matrix were complex? Wouldn't that be horrible? Who would ever do that? Well, we will. That's like the third to last class. Yeah, what you did in linear algebra is the setup, but the problems that we do are they're so much harder. We could spend a day on that. Complex eigenvalues. In linear algebra, what you did were Hermitian matrices, which only, well, hopefully you did these, only had real eigenvalues even though you had complex matrices. But your eigenvalues were real, your eigenvectors are complex. What if your eigenvalues are complex? That one's a nightmare. We actually have to look at that problem because it comes up. So this is our situation. So what are our linearly independent solutions? E to the alpha plus beta I times x.
Alpha minus.
Yee. Big X. Okay, so we're going to use Euler's formula in a moment, but not yet. So what I want to do is break this up because, right, exponents, I can do this. Can I write this one as e to the alpha x, e to the beta, on the right, I beta x. And then the next one would be e to the alpha x, or actually, I'm sorry, let me write it this way. Beta ix, sorry. Because that's going to be,
I like these.
no, you know what? I'm trying to think what's going to be the most, I'll just leave it as beta ix, sorry. We'll do that in a moment. And then what's this one? E to the negative beta ix. We'll group them in a moment. I don't want that to get in the way. Here my argument is theta, so here my argument is x. Alpha and beta are constants. You just calculate, 2 plus 3i, that kind of thing. But then times x. So that now means my horrible answer is now in the form y equals c1 e to the alpha x e to the beta ix plus c2 e to the alpha x e to the negative beta ix. Ugh, that is so not friendly because the problem had real coefficients. I'd really like my answer to look like real things. Okay, well at least e to the alpha x. That's okay. So can I factor that out of the problem?
Yes.
So that's not the problem, child. Okay, now let's use Euler's formula. Now, in my Calc 1 class, I derive all the hyperbolics. We don't need that right now, although they do come up occasionally in this class. So I might be well served to derive them a little bit in this class. If you remembered the hyperbolics, and by the way, most people, I hate to tell you, for forever everybody got the right definition, and then somewhere around the 80s and 90s they started dumbing down textbooks, going, oh, it's too complicated. So let's give an incorrect definition, and forevermore no one knows what they are. It's kind of ridiculous, but the hyperbolic cosine of x is the cosine of ix. That's what it is. That's real, therefore that's imaginary. If that's imaginary, then that's real. So if I asked you on your calculator, I want you to take the hyperbolic cosine of, let's keep it of 4. You all have a key on your calculator. You have an HYP key on your calculator. So everyone do this. Do the hyperbolic cosine. Oh, by the way, you need to be in radian mode, by the way, just to remind you. Anytime you do a calculation, you've got to be in radian mode. So do the hyperbolic cosine, and my screen now says COSH. That's how we say hyperbolic, of 4, and we get
27.
approximately 27 point. Wait a minute. So the cosine of 4i, where I is the square of -1, the cosine of 4i is 27. Yeah. We know that sine and cosine are limited to be between -1 and 1. Well, that's half true.
In the real.
That's only if I input a real angle. But if I input imaginary angle, I actually get the entire real number. Oh my goose, yeah. No, it is not true that everything you've ever been told is a lie. The truth has just been withheld. Yeah, most of the things you hold dearly may or may not actually be true. They're true in the real system, but we are going to venture in both directions. Now, your calculator, cheap calculator did this, like, what the heck did they do? Well, they're using Euler's formula. So I want to remind you that. And by the way, the hyperbolic sine is -I sine ix. So therefore, if I take the derivative of hyperbolic sine, I get back hyperbolic cosine, because the chain rule factor would be I is still a constant. And the derivative of this is this. These are their own derivatives, and then the difference of squares ends up being 1. That's called the hyperbolic Pythagorean theorem. That's actually part of the, E equals mc squared. That's part of the theory of relativity. He uses hyperbolic geometry, non-Euclidean, fourth dimensional, hyperbolic Pythagorean. It's scary if you go off into that realm. But how does this help me? Well, if I said to you, I want to manipulate this and do this stuff. Well, using Euler's formula, if I said, what is E to the, I know what E to the IX is, okay? But what if I make my angle itself, or let's say, if I said E to the I theta. If I said, let's make theta -IX. Make theta -IX. Then I have E to the I theta. I times -I is -I squared, or 1. And now that equals what? Cosine of -IX. I said, by the way, this is purely real. X is going to be real input with an imaginary angle, plus I sine -IX. Okay? Now here, I'm not going to go into a whole explanation, but you guys know odd and even functions.
Yes.
Cosine is an even function. Did I just miss? I said replace theta with -I. Okay. You all know cosine's an even function. So what does this equal?
Cosine of IX.
You know that sine is an odd function. So this equals, sine of ix. And that means this equals the hyperbolic cosine plus the hyperbolic sine. That's really an important identity that no one's ever seen in calculus, because they haven't, that 40 years that's been removed from calculus books. I don't know why. It is kind of important. Okay, now what if theta equals positive ix? Then what do I get? Then I get e to the what?
-X.
E to the -x equals cosine of ix plus I sine of ix, which is simply the hyperbolic cosine of x minus the hyperbolic sine of x. And here's where all the formulas in the calculus books come from. If I want to isolate the hyperbolic cosine of x, well, add this to this, and then hyperbolic signs cancel, and I get 2 hyperbolic cosines. Therefore, this is half of e to the x plus e to the negative x. That's the formula in every calculus book. That is not the definition. That's not even like the definition. That is a result of the definition and Euler's formula. That drives me crazy that any human being would think the definition of a hyperbolic function is an exponential function. No. It's a function of an imaginary input. And when you get to Calc 2 and you do series, the way you do the series for this is you do the series for cosine and replace x with ix, and you're done in like 10 seconds. It is so fast and easy. It's so cool. And then hyperbolic sine, if I take the difference of those two. So if you're wondering, how did your calculator come up with that crazy answer? When your calculator did the calculation, it actually calculated this. It's not working with imaginary numbers. So if I understand this, let's convert this to Euler's formula and let's do the exact same mathematics, and the answer is going to fall right into our lap. You're going to like this. It's not fun and it's not comfortable for most people because this is not an area of strength, because you may saw a little bit of this in a pre-calc class. You may not have seen any of it in a calculus class. In my linear algebra, we do the complex eigenvalues, eigenvector. We do that chapter of complex matrices. That's like the very last thing, because when you start your upper division, that's what they're going to start with. They're not going to start with the earlier stuff. So let's use Euler's formula. So what does this become? Let's just do this part, because that's already there. This would be C1 times the cosine of what?
Beta I.
So it's
Oh, cosine
it's the cosine of.
beta I.
So remember, it's e to the I theta. That's my theta.
Yeah.
So it's just the beta x. You're wanting to put the whole I in there. It's just the beta x. That's why when I was trying to rewrite, I was like, where should I stick the I? We'll figure it out later. And then what's the next term?
I sine.
Plus, I, where are we? We're still on this
Yeah.
one.
Sine
Plus
beta
I
A.
sine
Beta X.
beta x. Yeah, too many symbols here. Okay, and then,
Plus C2.
okay, just make sure I got that. And then C2, same thing. Cosine of, now we're doing this one, so it's
Negative beta X.
negative beta x
Plus.
Hope I did that right. How's that look? So my theta in Euler's formula, e to the I theta, my theta is the beta x. So we don't want to lose that. So I think I wrote these correctly. All right, let's distribute and gather terms. Oh, well, wait a minute, odd and even.
Mm-hmm.
Then this becomes C2 cosine beta x minus I sine beta x. Now when I gather terms, what do I got? I've got C1 plus C2 times the cosine of beta x. By the way, beta x is real. Beta x is real. Remember when we solved, I said to solve the quadratic, we got alpha plus beta I? Alpha and beta are real. It's the I that made it complex. But alpha and beta are absolutely real. That's not even a question. Then what? Plus I times C1 minus C2 sine beta x. Yikes. So now let's throw in the e, the original e. This is kind of scary looking. Now, we've made this remark before. When you're solving and you take a linear combination of your linearly independent functions, there are actually no rules governing the coefficients. Your coefficients can be complex. It's just your functions were not complex. Everybody understand that? Your coefficients can be anything and it wouldn't change anything. If you check an answer with a C1 and a C2, you're going to get the right answer whether C1 is real or imaginary or complex. It doesn't matter. So since C1 and C2 can be anything real or complex, I have a great idea. Let's just call it C3. What do you want to call this guy?
C4.
So now, when I have the two complex, horrible solutions, then can I rewrite my problem as y equals C1 That's what I just derived over there. What do you think? That doesn't look quite as scary, does it? And that's the form you want. You do not want anything that looks like this, because I just showed they're identically equal. But not C1 and C2 based on what we did, because of my final result. Now, when you're doing the problem, you're just going to call them C1, C2, because you're not going to do the derivation again. What if? What if? Because this is one of the most important results that I'm about to show you. What's my auxiliary equation here?
n2 plus 1.
M2?
Oh,
How about
n
M squared?
N squared, sorry.
M2 is the second solution. Man, that can't be factored, so I can't answer this, right? There's no solution, right? Well, there are two solutions.
2y.
Oh my gosh. How about if I thought of it this way? 0 plus or minus 2i. Oh, so tell me about that guy. This is 1. So really all I have are what? Sine and cosine. So what's y1? Cosine of 2x. What's y2? Sine of 2x. Oh my gosh, that was easy. I mentioned this last week, and some of you looked at me with the whole side-eye thing. I said, if you're getting sine and cosine, that means everything you did was purely imaginary. Remember me saying that? I just proved it. If your roots are purely imaginary, you're going to get sine and cosine. If your roots are complex, and when we say complex in this context, we mean there's a mixture of real and imaginary, then you get the ugliest one. You get a real exponential times your sine and cosine. If your results are purely real, then your alpha plus beta, the beta is 0. And you're only going to get things that look like this. So purely real solutions look like exponentials, purely imaginary look like sine and cosine, and the mixture looks like that. But you never have to do the derivation ever again. You go directly to the answer. That's what I just did. Because isn't my beta 2? And is this one easy enough to check? Yeah, isn't that cool that you got? I had no idea it'd be that simple. Well, I couldn't have told you this without us doing all the previous stuff, because I actually have to get imaginary roots. But how do I go from imaginary roots to sine cosine? Well, that's what all of this was about. But I want you to go directly to the results now. I don't want you to do any part of the derivation. So therefore, if your answer is of the form, 5 plus or minus 6i, then you say e to the 5x, and then it's sine and cosine of 6x. Right? It's real simple. And the check is actually simple, because we are doing real valued functions. We just happen to have imaginary numbers in the roots of the auxiliary equation. But I still want to represent my answer with real valued functions. I don't want functions of imaginary things, or it's too difficult to work with. It's not incorrect. But this is way too hard to work with. Sine and cosine are just much, much simpler. And in the long run, you're going to get the same answer. Okay, any question on this? The crazy stuff?
I'm too...
So what I ask you to do is solve a whole bunch of problems where really all you got to do is factor the auxiliary equation and then write the answer down. I don't need you to do any derivation. I need you to figure out the roots.
Oh, so all of this was the derivation for the imaginary to, or real to imaginary.
Exactly. Now, our primary concern is to be able to do any version of a second order differential equation. Why? Because it produces a quadratic auxiliary equation. I don't care what the numbers are, everybody here can absolutely 100% of the time do that one pretty simply. I showed you what can happen if it's higher order, particularly if one of your roots is a 0. That's not a harder problem. I'm not going to just give you some generic fourth order thing where you have to factor big gnarly fourth degree polynomial. That's too much work. It's too difficult. That's not calculus at that point. That's something completely different. So every problem we get, I guarantee you, you will be able to factor it. That will not be an issue. It'll be something you can easily factor, okay? And then from that, you can then answer the question. Yeah.
Can you explain again how you get to I to y1 and y2?
How I got that?
Yeah, to y1 and y2.
Oh, okay. Well, first of all, doesn't this say that n squared has to be -4?
Yes.
So then m is plus or minus the square root of -4, which is plus or minus Because it's the square root of negative one thing.
And how do you get 1, 1 equals cosine?
Because going back to, where did I write the final version? Sorry.
In the blue.
Oh, right.
The date, over there in the left.
Way left.
In the blue.
Oh, okay. Because we had 0 as the real part, this term would be 1. So we don't even need it. So now I'm down to just this and just this.
Okay.
But the beta is not 2i, beta is 2. It's alpha plus beta I. So the beta is a 2. That's why it's 2x. This will always be real. Based on everything I said, it didn't start off real, but became real by me manipulating and using Euler's formula. That's one of the reasons Euler's formula is so useful, so powerful. So even if you have no background, I'm not asking you to derive these. This type of derivation will come up more than once in this course, and when we do it again in a different context, you'll say, oh yeah, it looks a lot like what we did here. But it's really only, as long as you understand the route and I got to the final answer and you go, okay, that makes sense to me, but we can start at the end. We just did some applications recently where I said you could kind of jump into the middle rather than rederive everything, but it's important that you understand the derivation. Will you ever reproduce it? Yeah, probably in another class, but not in this class. Once we derive something, I don't want you to keep rederiving it. It's not efficient, because you might come up with something else. Kind of need you to be right.
Are we ever gonna get like an alpha value? Like a value?
Well, yeah, let's do one.
Oh, shit.
Yeah, careful what you wish for, right? So let's do d squared y dx squared plus, I don't know, how about 4 dy dx plus 29y equals 0. How's that? So my auxiliary equation does this factor? 29 is
Huh.
probably not that.
Nah.
No. Well, if I completed the square, there's one way to do it. Or I can just use my quadratic formula. In either case, I'm going to get m equals what? -2 plus or minus 5i.
Yeah.
I'm being lazy. Yes, I use the quadratic formula, but I can usually do things faster. I do everything I do algebraically, I usually do faster than the standard way. So I have 2 roots, and so the question was, will we ever get something? We just did. We have real plus or minus imaginary. Can you write the solutions now without doing any in between? That's what I want you to do. So let's write our 2 linearly independent solutions. This will be the last thing we do. That's what they're going to look like. So what goes here?
Whatever alpha is times x.
So
Negative 2x.
negative 2x on both of them. What's going to go here? On both of
5x.
them, 5x. Everybody got it?
Yeah.
Was that hard to do? Hopefully not. The worst one will be when you have a coefficient that's not a 1, and now you got to use your quadratic formula. Oh my gosh.
Oh.
So another add 15 seconds to the length of the problem. No, there's no problem of this nature that really should be giving you trouble, to be honest. These got to be pretty clean.
Are you saying that when you complete the square, you immediately get that answer?
So that's
Do
like
you immediately get the
that's
answer?
awesome.
After you completed the square, m plus 2 squared plus 5 squared, you can literally just plug it into m equals -2 plus or minus 5i.
Well, then I would get.
Is that a rule that's going to be like for every single completing the square, you can automatically?
You don't have to use complete square. I just did because I'm lazy.
Well, I mean,
When I say you go, you can use complete the square because you're lazy. Yeah, because I can get the answer in the next step rather than 3 algebra, 4 algebraic steps. No, just use your quadratic formula. You're going to get that.
Oh, I see.
These are the roots regardless of the route you took.
Right. But like still, when you complete the square, you immediately get the roots like that?
Yeah,
That's really crazy. Because that's like a...
cool stuff. All right, let's go ahead and stop. I'm going to do the roll thing real quick. I'm going to